Picture this: you're staring up at the night sky, and for a fleeting moment, you realize just how small we truly are in the grand scheme of the cosmos. But what if I told you that the universe is far from silent, far from still? In fact, it's teeming with events so extraordinary, so mind-bending, they could rewrite everything we know about space and time. And here's the kicker: many of these cosmic spectacles aren't centuries away. They're happening sooner than you might think. From colliding black holes to rogue planets hurling through the void, the next few decades could bring us front-row seats to some of the most awe-inspiring events in the history of the universe. So, are you ready to have your mind blown? The universe has always been a master storyteller, spinning tales of creation and destruction on scales we can barely comprehend. But now, for the first time, we're not just passive observers. With cutting-edge technology and the relentless curiosity of scientists, we're on the brink of witnessing cosmic events that were once the stuff of science fiction. Imagine watching a star being torn apart by the gravitational pull of a supermassive black hole, or witnessing the birth of an entirely new galaxy. These aren't distant fantasies, they're predictions grounded in the latest research, and they're coming to a universe near you. That's exactly what we're diving into today: 25 cosmic events that could shake the foundations of astronomy and leave us questioning our place in the cosmos. Some of these phenomena will challenge our understanding of physics, while others might even hint at the existence of life beyond Earth. And the best part: you won't have to wait a lifetime to see them unfold. Whether it's a once-in-a-millennium asteroid flyby or the explosive death of a nearby star, the universe is about to put on a show, and you're invited. So buckle up, because we're about to embark on a journey through space and time, exploring events that will leave you in awe of the universe's endless wonders. Let's begin with one of the most anticipated cosmic events in modern astronomy: the eventual explosion of Betelgeuse. This colossal red supergiant, which forms the shoulder of the Orion constellation, isn't just another twinkling dot in the night sky. It's a ticking time bomb, a star on the verge of going supernova. And when it does, it'll be a spectacle unlike anything humanity has witnessed in recorded history. Right now, Betelgeuse is a dying star, having burned through its nuclear fuel at an astonishing rate. It's already so massive that if you placed it at the center of our solar system, its outer layers would stretch past the orbit of Jupiter. But what's truly staggering is the sheer energy it's about to unleash. When Betelgeuse finally collapses under its own weight, the resulting supernova could shine brighter than a full moon, casting shadows at night and even being visible in broad daylight for weeks. The timing, though, is the big question. Astronomers estimate it could happen anytime within the next 100,000 years, which, in cosmic terms, means it might as well be tomorrow. Recent observations only add to the mystery. In late 2019, Betelgeuse suddenly dimmed, losing nearly 2/3 of its usual brightness. For a brief moment, the world held its breath. Was this the beginning of the end? While the star has since returned to its normal glow, the event sparked heated debate. Some scientists believe it could be a sign of impending collapse, while others argue it's just part of the star's natural variability. What makes Betelgeuse so fascinating isn't just the spectacle, it's the scientific goldmine. A supernova this close, just 640 light-years away, would give astronomers an unprecedented look at the death throes of a massive star. We could witness the formation of heavy elements like gold and platinum in real time, study neutrino bursts, and even test theories about how supernovas shape the cosmos. And let's not forget, the last time a nearby star went supernova, in 1604, it was visible for weeks without telescopes. Imagine what we could learn with today's technology when Betelgeuse finally takes its final bow. But here's the kicker: despite all our advances, we still can't predict exactly when it will happen. It could be next year, next century, or millennia from now. And that unpredictability is part of what makes astronomy so thrilling. We're not just passive observers, we're detectives piecing together clues from a star that might already be gone. Its light still traveling toward us, carrying the secret of its fate. When Betelgeuse does explode, it won't just be a dazzling light show. It'll be a moment that redefines our understanding of the universe. When Betelgeuse finally explodes, the cosmic fireworks won't just be a visual spectacle, they'll be a full sensory experience for astronomers. Picture this, a sudden burst of light so intense it outshines every star in our galaxy combined, visible even during the day for weeks. But beyond the dazzling display, the real scientific treasure lies in what we'll detect. As the star collapses, it will unleash an avalanche of neutrinos, tiny, ghostly particles that rarely interact with matter. These elusive messengers will reach Earth hours before the light does, giving detectors like Super Kamiok and in Japan an unprecedented chance to study the inner workings of a dying star in real time. Now let's address the elephant in the room. Could this supernova pose any danger to us? Despite what sensational headlines might suggest, the answer is a resounding no. Betelgeuse is close enough to put on a show, but far enough to keep us safe. The myth that its explosion could bathe Earth in deadly gamma rays is just that, a myth. Even at 640 light-years away, any high-energy radiation would be diluted to harmless levels by the time it reaches us. In fact, the last supernova observed in our galactic neighborhood, Kepler's star in 1604, didn't harm life on Earth, it simply inspired awe. What's truly exciting is the scientific windfall this event will provide. For the first time in history, we'll have telescopes capable of capturing every stage of a supernova's evolution, from the initial shockwave to the formation of a new nebula. Instruments like the James Webb Space Telescope could analyze the chemical fingerprint of the explosion, revealing how elements like carbon, oxygen, and iron are forged in stellar furnaces. We might even witness the birth of a neutron star or black hole, an object so dense it bends the fabric of space itself. And let's not forget the cultural impact. Imagine stepping outside months after the explosion and seeing a new, glowing cloud where Betelgeuse once shone. Ancient civilizations recorded supernova as omens. Future generations will study this one as a Rosetta Stone for stellar physics. The data collected could answer lingering questions about how massive stars shape their surroundings, how heavy elements spread through galaxies, and even how life itself might owe its existence to the ashes of long-dead stars. So while Betelgeuse's demise won't threaten Earth, it will gift us something far more valuable, a front-row seat to the universe's grand cycle of destruction and creation. And when that day comes, you'll know you're witnessing a once-in-a-species event, one that will echo through scientific textbooks for centuries to come. While Betelgeuse's explosion remains a cosmic question mark, there's another celestial event with a far more predictable timetable, one that's set to shake up our skies in just a few short years. Welcome to Solar Maximum, the upcoming peak of Solar Cycle 25, expected to hit its crescendo in 2025. This isn't just another routine phase of the sun's activity. It's a period of heightened solar drama that could bring everything from dazzling auroras to potential disruptions for our tech-dependent world. At the heart of this phenomenon are sunspots, those dark, tempestuous patches on the sun's surface where magnetic fields tangle like knotted ropes. During solar maximum, these sunspots multiply, unleashing solar flares and coronal mass ejections with startling frequency. Think of it as the sun's version of a storm season where space weather turns volatile. The most powerful flares can release energy equivalent to billions of hydrogen bombs in mere minutes, hurling radiation and charged particles across the solar system. Now here's where things get thrilling for skywatchers. When these charged particles collide with Earth's magnetic field, they ignite auroras, those ethereal curtains of light that dance near the poles. But during a solar maximum, the show doesn't stay confined to the Arctic and Antarctic. Historic storms have pushed auroras as far south as Cuba and Hawaii. Imagine stepping into your backyard in places like New York or Madrid and seeing the northern lights ripple overhead, painting the night in otherworldly greens and purples. It's a rare treat that transforms the sky into a living canvas, yet there's a flip side to this cosmic spectacle. The same solar tantrums that create breathtaking auroras can also wreak havoc on our technology. Take the Carrington event of 1859, the most intense solar storm on record. Telegraph systems, the cutting-edge tech of that era, sparked and caught fire, while auroras blazed so brightly they woke people up, mistaking them for dawn. Fast forward to today, and a storm of that magnitude could knock out satellites, disrupt GPS, and even trigger widespread power grid failures. A 2012 near miss, where a Carrington-level ejection narrowly missed Earth, served as a stark reminder of our vulnerability. But before you start stockpiling batteries, here's the reassuring part. Scientists are better prepared than ever. Networks of satellites like NASA's a Solar Dynamics Observatory monitor the sun around the clock, giving us crucial hours or even days of warning. Power companies and spacecraft operators now have protocols to shield critical infrastructure from the worst effects, and for the rest of us, the rewards far outweigh the risks. Solar Maximum is a chance to witness one of nature's most dazzling displays, a reminder that even our seemingly placid sun has moments of wild, untamed beauty. So mark your calendars for 2025. Whether it's the auroras or the science, this is one cosmic event you won't want to miss. For centuries, Mars has been a tantalizing mystery, a rust-colored world that's teased us with the possibility of life beyond Earth. And now, we're on the verge of an unprecedented milestone that could finally crack the red planet's biggest secrets, the Mars Sample Return mission. This ambitious collaboration between NASA and the European Space Agency aims to do something humanity has never attempted: launching rocks and soil from another planet back to Earth. If all goes according to plan, by 2033, scientists could be holding pristine pieces of Mars in their labs, searching for clues that might rewrite the story of life in our solar system. The star of this cosmic heist, NASA Perseverance rover, which has been scouring Jezero crater since 2021, collecting samples from what was once an ancient river delta. Think of it as an interplanetary detective, carefully sealing Martian dirt and rocks into ultra-sterile tubes, each one a potential time capsule from a time when Mars may have been warm, wet, and hospitable to life. But here's the catch. Getting these samples home requires a jaw-dropping sequence of engineering feats. First, a second spacecraft will land near Perseverance, deploy a small rocket, and load the samples. Then, that rocket must launch from Mars, a first in history, rendezvous with an orbiting spacecraft, and begin the long journey back to Earth. Every step is a high-stakes ballet with zero room for error. What makes these samples so valuable? They could contain chemical fingerprints or even fossilized traces of ancient microbial life. On Earth, we've found bacteria thriving in the harshest environments, deep in mines, inside volcanoes, even floating in the upper atmosphere. If Mars once had similar extremophiles, their remnants might still be locked in these rocks, but with that potential comes heated debate. Some scientists warn about the risk of backward contamination, the slim but terrifying chance that a Martian organism, however primitive, could hitch a ride to Earth with unpredictable consequences. That's why the return mission includes multiple layers of containment, with samples quarantined in a high-security lab for years before being released for study. It's not just about safety, it's about preserving the integrity of the science. A single stray Earth microbe could ruin decades of research by masking potential Martian biosignatures. And beyond the technical challenges lie ethical questions. Do we have the right to bring pieces of another world home? Could we accidentally erase the very evidence we're searching for? Despite the debates, the payoff could be astronomical. Confirming life existed on Mars even billions of years ago would prove we're not alone in the universe, that life can spark anywhere conditions are right. And if the samples come back blank, that answer would be just as profound, forcing us to ask why Earth, amid countless similar worlds, became the exception. Either way, this mission isn't just about retrieving rocks, it's about bringing home a piece of the cosmic puzzle that's eluded us for generations. And in less than a decade, we might finally have our answer. While Mars dominates headlines in the search for alien life, another world in our solar system hides perhaps an even more promising secret. Enter Europa, Jupiter's enigmatic moon, a frozen world with a subterranean ocean that could hold twice as much water as all of Earth's seas combined. And in October 2024, NASA Europa Clipper spacecraft is set to embark on a daring mission to uncover whether this distant moon could harbor the ingredients for life. What makes Europa so special? Beneath its cracked, icy shell, a surface that looks like a celestial spiderweb, lies a vast, global ocean kept liquid by the relentless gravitational squeezing of Jupiter. But here's the twist: this isn't just any ocean. Scientists believe it could be interacting with a rocky seafloor, creating hydrothermal vents similar to those on Earth where life thrives in complete darkness. These vents, spewing mineral-rich plumes, might just be the cosmic kitchens where Europa's potential microbes could cook up their existence. Now, the Europa Clipper isn't just another orbiter. It's a high-tech detective armed with 9 cutting-edge instruments designed to sniff out signs of habitability. From radar that will map the thickness of Europa's icy crust to spectrometers analyzing the chemistry of its mysterious plumes, this spacecraft is built to answer one burning question: is there life in these waters? One instrument, aptly named the S-Surface Dust Analyzer, will catch and examine tiny grains ejected from Europa's surface, hunting for organic molecules, the building blocks of life as we know it. But the real game changer lies in the mission's strategy. Unlike traditional orbiters, the Clipper won't circle Europa directly. Instead, it will perform a series of close flybys, swooping as low as 15 miles above the surface to minimize exposure to Jupiter's punishing radiation belts. This dance around the moon will allow it to map nearly the entire surface while searching for those telltale plumes geysers that might be squirting Europa's ocean water into space, offering a free sample for the Clipper to analyze. The implications are staggering. If the mission detects even simple organic compounds or chemical imbalances suggestive of microbial metabolism, it would revolutionize our understanding of life's potential in the cosmos. Some researchers speculate that Europa's ocean could host ecosystems akin to Earth's deep-sea vents, where organisms derive energy not from sunlight but from chemical reactions. Others go further, suggesting that tidal forces might have created a network of interconnected liquid pockets within the ice itself, micro-environments where life could have gained a foothold. Of course, not everyone is convinced. Skeptics argue that without direct access to the ocean, any evidence will remain circumstantial. That's why NASA is already planning a follow-up, a lander that could drill through the ice or sample plume material directly. But for now, the Europa Clipper represents our best shot at peering into an alien ocean without getting our feet wet. When it arrives at Jupiter in 2030, after a 6-year journey, it could rewrite the textbooks, proving that life isn't a fluke of Earth but a cosmic inevitability. And that's a discovery worth waiting for. Remember 2020's Christmas star, that breathtaking moment when Jupiter and Saturn appeared to merge into a single brilliant point of light? That was the Great Conjunction, a celestial dance that hadn't been that close in nearly 8 centuries. But here's the good news: you won't have to wait another 800 years for an encore. These gas giants are cosmic clockwork, and their next intimate meeting is already on the horizon. The magic behind these conjunctions lies in their orbits. Jupiter, the solar system's speedster, laps the Sun every 12 years, while slower, ringed Saturn takes 29. Picture two race cars on different tracks, one zipping around every few laps while the other lumbers along. Every 20 years or so, Jupiter catches up to Saturn from Earth's perspective, creating that stunning visual overlap. But not all conjunctions are created equal. The 2020 event was special because it brought the planets closer than they'd been since the Middle Ages, just 1/10 of a degree apart, or roughly the width of a dime held at arm's length. So when's the next show? Mark your calendars for March 15, 2080. While this upcoming alignment won't be quite as tight as 2020's, it'll still be a jaw-dropper, about 1 degree apart or 2 full moon widths. And unlike the twilight spectacle of 2020, this one will unfold against a dark midnight sky, offering stargazers an even clearer view. Future generations can expect similar celestial handshakes roughly every 2 decades, with particularly close pairings in 2040, 2060, and 2080. But these events aren't just astronomical curiosities, they're cultural touchstones. History shows that close conjunctions often spark wonder, superstition, and even panic. The 2020 event revived claims of it being the biblical Star of Bethlehem, while fringe groups insisted it signaled apocalyptic change. In 1623, a similarly tight conjunction coincided with the 30 Years' War, leading some to blame the planets for earthly chaos. Even today, as science demystifies these alignments, their power to captivate remains. Imagine 2080's conjunction inspiring art installations, global observation parties, or viral augmented reality experiences we can't yet fathom. What makes these events so enduring isn't just their predictability, it's their reminder that the universe operates on scales both grand and intimate. A child born during 2020's Christmas star could witness 4 more conjunctions in their lifetime, each a chance to reflect on how far we've come in understanding the cosmos. And who knows, by 2080, we might have telescopes powerful enough to spot storms on Saturn or volcanic plumes on Jupiter's moons during these alignments, turning a beautiful sky-watching moment into a full-blown scientific bonanza. The planets will keep dancing and we'll keep looking up. In October 2017, astronomers spotted something that shattered our understanding of cosmic visitors. A strange, tumbling object hurtling through our solar system at breakneck speed. Named Oumuamua, Hawaiian for scout, it was the first confirmed visitor from another star system. But this wasn't your typical asteroid or comet. Its bizarre shape, possibly cigar-like or pancake-flat, combined with its unexpected acceleration, sparked debates that raged from academic journals to late-night talk shows. Was it a fragment of a shattered planet, a cosmic iceberg venting gas, or, as some dared to suggest, could it have been alien technology sailing past Earth? Fast forward to today, and the mystery of Oumuamua remains unsolved. But here's what we do know: it won't be the last interstellar traveler to drop by. In fact, with telescopes like the upcoming Vera Rubin Observatory coming online, we're on the verge of detecting dozens of these cosmic nomads, perched atop a mountain in Chile and equipped with the largest digital camera ever built. Rubin will scan the entire visible sky every few nights, spotting faint, fast-moving objects earlier and more frequently than ever before. And that means the next Oumuamua could be discovered any day now. The real question is, what will we find? Some scientists theorize these visitors could be shards from distant planetary collisions, hurled into the void by gravitational chaos. Others suggest they might be frozen remnants of other solar systems, carrying chemical blueprints of alien worlds. Then there's the tantalizing possibility of spotting something far stranger, an object with such peculiar properties like unnatural reflectivity or trajectory adjustments that it defies easy explanation. Critics argue that jumping to extraterrestrial conclusions is premature, pointing out that Oumuamua's behavior, while odd, could still have natural explanations we simply haven't uncovered yet. But that's exactly why the next detection matters. Each new interstellar object is a cosmic detective story, offering clues about the building blocks of other star systems, and just maybe hints of civilizations we've yet to meet. Imagine this: one night, Rubin's cameras pick up an object moving too fast to be bound by the sun's gravity. Telescopes worldwide swing into action, analyzing its color, rotation, and composition. Maybe it's another rocky oddity tumbling silently through the dark, or perhaps it's something else entirely, an artifact so unusual it changes how we see our place in the universe. Either way, every new visitor brings us closer to answering an age-old question. Are we alone, or is the cosmos far stranger and far more crowded than we ever dared to dream? The moon isn't just Earth's celestial companion anymore. It's about to become humanity's first off-world construction site. NASA's Artemis program aims to plant boots on lunar soil again by 2026, but the real game changer comes next: a permanent moon base set to rise in the 2030s. This won't be the flag and footprint mission of the Apollo era. Imagine sprawling, inflatable habitats buried under lunar regolith for radiation protection, powered by solar arrays and possibly even small nuclear reactors. Astronauts could stay for months conducting experiments, harvesting local resources, and testing the technologies that might one day sustain us on Mars. At the heart of this ambitious plan is Starship, SpaceX's colossal next-generation rocket. Designed to carry 100 metric tons of cargo, equivalent to a medium-sized house, to the lunar surface, it's the only vehicle capable of delivering the bulky habitat modules and heavy equipment needed for a sustained presence. Picture this: a fleet of starships landing near the moon's south pole, where permanently shadowed craters hold precious water ice. That ice isn't just for drinking. Split into hydrogen and oxygen, it becomes rocket fuel, effectively turning the moon into a cosmic gas station for deeper space missions. But building a moon base isn't just an engineering challenge, it's a legal and political tightrope. The 60-year-old Outer Space Treaty prohibits nations from claiming celestial bodies, but it's silent on whether private companies can mine resources or how close rival bases can operate without causing tensions. China, already planning its own international lunar research station by 2035, could spark a new space race, one where the finish line isn't just planting a flag, but establishing permanent footholds with economic and strategic value. Some fear a lunar Wild West where competing bases trigger conflicts over prime real estate near water sources or sunlight-rich peaks. Yet for all the potential pitfalls, the scientific payoff could be revolutionary. A moon base would serve as the ultimate testbed for Mars-bound tech, from closed-loop life support systems that recycle every drop of water to 3D-printed shelters made of lunar dust. Astronauts there would experience just 1/6 of Earth's gravity, offering crucial data on long-term health effects before the year-plus journey to the Red Planet. And let's not forget the pure exploration, the chance to study pristine lunar lava tubes, some wider than city blocks, which could provide natural shelters for future colonies. The moon base represents more than just a stepping stone. It's a declaration that humanity's future isn't confined to Earth. By the 2040s, if all goes well, rotating crews of scientists and engineers could be working under the dim glow of Earthlight, their every breakthrough paving the way for the next giant leap. And this time, we're not just visiting, we're staying. Voyager 1 and Voyager 2, our most distant emissaries, are slowly fading into silence. These twin spacecraft, launched in the golden summer of 1977 with technology less powerful than your smartphone, are now drifting beyond the edge of the sun's influence, their nuclear batteries draining year by year. By the 2030s, their final signals will flicker out, leaving humanity's first interstellar messengers to drift forever in the void. But what they've taught us along the way has rewritten astronomy textbooks. Think about this: when these probes launched, we didn't even know if planets outside our solar system existed. Now, thanks in part to Voyager's data, we've confirmed thousands. Their most revolutionary discovery came in 2012, when Voyager 1 punched through the heliosphere, the invisible bubble where the Sun's magnetic field shields us from interstellar radiation. For the first time, we sampled the raw stuff between stars, finding it far more turbulent and densely packed with particles than anyone predicted. Voyager 2 followed in 2018, revealing that this cosmic shoreline isn't uniform but wrinkled and dynamic like a crumpled blanket. Then there are the golden records, humanity's time capsules bolted to each spacecraft's flank. Etched with greetings in 55 languages, the sounds of thunderstorms and whales, even the brainwaves of a person in love, they were a hopeful message to any civilization that might one day find them. Today, those records feel like relics of a more optimistic era, a time when we dreamed of handshakes with alien cultures rather than dystopian first contact scenarios. Which raises a fun question. If we launched a new message to the stars tomorrow, what would we include? A TikTok compilation, Bitcoin white papers, the complete works of Taylor Swift? The truth is, any modern record would reveal just how much we've changed, not just technologically, but in how we see ourselves in the cosmos. Voyager's records were a love letter to Earth's diversity. Today, we might send schematics for AI or warnings about climate collapse. As their power wanes, the Voyagers will become cosmic ghosts, silent but still moving. In 40,000 years, Voyager 1 will drift within 1.6 light-years of a star in the constellation Camelopardalis. Voyager 2, it's headed toward Sirius, though it won't get close for nearly 300,000 years. By then, humanity might be extinct or spread across the galaxy. Either way, these little probes will still be out there, carrying our whispers into eternity, proof that once we reached for the stars with nothing but analog guts and boundless curiosity. Their final signals won't just mark an ending, they'll remind us how far we've flown on the wings of questions. Imagine a fleet of tiny spacecraft, no larger than a postage stamp, hurtling through the void at 20% the speed of light, bound for the closest star system to our own. This isn't science fiction, it's the audacious vision of Breakthrough Starshot, a project that could see humanity's first interstellar probes reach Proxima Centauri by the year 2050. At the heart of this mission lies an ingenious propulsion technology, light sails. Picture wafer-thin probes, each weighing just grams, propelled not by rocket fuel, but by the gentle yet relentless push of powerful Earth-based lasers. These lasers, focused into a beam 1,000,000 times more intense than sunlight, would accelerate the probes to a staggering 60,000 kilometers per second in mere minutes. It's a concept that sounds straight out of Star Trek, yet physicists argue it's one of the few feasible ways to cross the mind-bending 4.37 light-years to our nearest stellar neighbor within a human lifetime. But here's the catch: surviving the journey isn't guaranteed. Even a grain of space dust struck at such speeds could obliterate a probe instantly. That's why Starshot's team envisions sending not one, but thousands of these nanocraft, hoping that at least a handful survive the interstellar gauntlet. Each probe would carry a minuscule camera, computer, and communications system, powered by a tiny nuclear battery. Their target, Proxima Centauri b, an Earth-sized exoplanet orbiting within the star's habitable zone, where temperatures might allow liquid water and just maybe life. The scientific payoff could redefine astronomy. If even one probe succeeds, it might beam back the first close-up images of an alien world, perhaps revealing continents, oceans, or atmospheric details. But critics warn we shouldn't hold our breath. At such speeds, the probes would zip past Proxima Centauri in mere hours, snapping photos in a frantic blur. Transmitting data back to Earth across 4 light-years with a laser the size of a fingernail would require engineering miracles. Some scientists fear we'll get nothing but silence, the probes reduced to cosmic shrapnel by interstellar hazards we can't yet predict. Then there's the philosophical debate. Even if we capture a single pixelated glimpse of Proxima b, what then? A blurry image might ignite more questions than answers, fueling decades of speculation. Others counter that the mere attempt proving we can reach another star within a generation would mark a leap as profound as the moon landing. It's a gamble with astronomical stakes, but one that could redefine humanity's place in the cosmos. After all, the first steps toward the stars were never going to be easy, but they might just be possible. For decades, scientists have been chasing a ghost, one that makes up 85% of the universe's matter yet refuses to show itself. Dark matter, the elusive substance that bends light and sculpts galaxies, remains cosmic hide-and-seek champion, but the game might finally be turning in our favor. Deep underground, in former gold mines and beneath mountain ranges, a new generation of detectors is waiting to catch the uncatchable. Leading the charge is LUX Zeppelin, or LZ, a vat of liquid xenon buried a mile beneath South Dakota's Black Hills. Here, shielded from cosmic rays by layers of rock, scientists hope to spot the faintest flicker of a dark matter particle colliding with a xenon atom. The setup sounds simple, but the scale is staggering: 10 metric tons of ultra-pure xenon, chilled to -100 degrees Celsius, watched over by sensors so sensitive they could detect a single photon. The quarry, WIMP, weakly interacting massive particles, theoretical heavyweights that could explain dark matter's gravitational grip without ever interacting with light. Yet WIMP aren't the only players. Enter Action's hypothetical particles so lightweight they were once dismissed as cosmic afterthoughts. Unlike their burly WIMP cousins, Actions would reveal themselves through subtle electromagnetic quirks, converting into microwaves in strong magnetic fields. Experiments like ADMX in Washington state are tuning giant radio receivers to hunt for these whisper-thin signals, turning entire laboratory cavities into cosmic action scanners. But here's the twist: what if the universe is playing a trick on us? After 30 years of increasingly sensitive searches, from Italy's Gran Sasso lab to Antarctica's ice cube, dark matter remains stubbornly invisible. Some theorists argue we've been chasing the wrong phantom altogether. Modified Newtonian dynamics, or MUND, suggests gravity itself behaves differently at galactic scales, no invisible matter required. It's a radical idea, one that rewrites Einstein's equations, but it neatly explains why some galaxies rotate as if they're glued together despite lacking dark matter's gravitational glue. The stakes couldn't be higher. If detectors like LZ or the upcoming Darwin project in Europe catch a WIMP or Action, it would rank among the greatest scientific breakthroughs of the century, finally revealing the hidden architecture of the cosmos. But if they come up empty, we might face a cosmic identity crisis, forced to admit that the universe's dominant form of matter is something far stranger than we ever imagined. Either way, the hunt is pushing our technology and our imaginations to the brink, and that's what makes this search so thrilling. We're not just solving a puzzle. We're rewriting the rules of reality itself. While we often think of the cosmos as a place of slow, stately movements, sometimes it delivers a spectacle of staggering violence, and none is more dazzling than a kilonova, the explosive collision of two neutron stars. Right now, in the Milky Way, these city-sized remnants of dead stars are drifting toward inevitable collisions, locked in gravitational dances that will end in cataclysmic embraces. Statistically, there's a 1% chance per decade that such an event will occur close enough for us to witness its full glory. And if it does, the aftermath could rewrite our understanding of where the universe's most precious elements come from. Picture this: two neutron stars, each so dense that a teaspoon of their material weighs 1 billion tons, spiral inward at nearly the speed of light. When they finally collide, the impact unleashes energies beyond comprehension, for a brief moment outshining entire galaxies. The explosion, known as a kilonova, blasts jets of material packed with free neutrons into space. These neutrons bombard surrounding atoms, creating rapid nuclear reactions that forge heavy elements like gold, platinum, and uranium in seconds. That's right, the wedding ring on your finger or the platinum in your phone might owe its existence to a cataclysm like this millions of years ago. but the scientific payoff isn't just in the glitter. A nearby kilonova would send ripples through space-time itself, gravitational waves detectable by observatories like LIGO and Virgo. These waves could reveal the exact moment the neutron stars merged, letting us watch in real time as matter is compressed into exotic states we can't recreate on Earth. Some theories suggest the collision might even birth a magnetar, a neutron star with a magnetic field so powerful it could erase credit cards from halfway across the galaxy. The real treasure, though, would be the light show. Unlike supernova, which fade over weeks, kilonovae blaze with a distinctive blue hue from radioactive decay before shifting to infrared as heavier elements form. Telescopes worldwide would scramble to capture this chromatic evolution, decoding the chemistry of cosmic alchemy in action. We might finally pinpoint how much of the universe's gold is made in these events, and whether they're the universe's primary foundries for elements essential to life. Of course, nearby, in cosmic terms, means within a few 100,000 light-years, close enough for detailed study but safely distant from Earth. A kilonova within our own solar system would be disastrous, showering us with deadly gamma radiation. But at the Milky Way's edges, it'd be the ultimate fireworks display, a once-in-a-species chance to witness the furnace where the universe forges its most precious metals. So keep your eyes on the sky and your telescopes tuned. When neutron stars tango, the universe doesn't just put on a show. It reveals the origins of everything valuable we've ever known. Elon Musk doesn't just want to visit Mars, he wants to build a bustling city there, complete with suburbs, factories, and maybe even the first interplanetary Starbucks. SpaceX's audacious plan, establishing a self-sustaining colony of 1 million people by 2050. It sounds like science fiction, but the blueprints are already taking shape, and they're as ambitious as they are controversial. Picture this: geodesic domes stretching across the rusty Martian plains, their translucent shells filtering harsh radiation while maintaining Earth-like air pressure inside. These wouldn't be flimsy tents, they'd be multi-layered fortresses, reinforced with locally mined materials and topped with solar arrays to harness the weak Martian sunlight. Early settlers might live in prefab modules hauled from Earth, but the long-term vision is far wilder. Imagine 3D printers churning out habitats from compacted Martian soil, or lava tubes, natural tunnels carved by ancient volcanoes, being repurposed as underground metropolises shielded from cosmic rays. Then there's the elephant in the room: terraforming. Musk has floated the idea of nuking Mars poles to release trapped carbon dioxide, thickening the atmosphere to trap heat and melt ice caps. It's a flashy headline grabber, but scientists aren't convinced. Even if we vaporized every ounce of CO2 on Mars, the atmosphere would still be a fraction as dense as Earth. Plus, without a magnetic field to protect it, solar winds would strip away any progress over centuries. The reality: future Martians might spend their entire lives indoors, trading open skies for VR projections of Earth's forests and oceans. But let's talk about the real hurdle: getting people there and the ethics of asking them to stay. Early missions will almost certainly be one-way trips, a fact SpaceX dances around with euphemisms like permanent residency. Sure, volunteers might sign up eagerly, but what happens when the novelty wears off? Imagine realizing too late that low gravity has weakened your bones irreversibly, or that a dust storm has severed your only supply line. And who governs this fledgling society? Will Martian settlers be bound by Earth's laws, or will they draft their own, potentially creating the first off-world dictatorship? Of course, where there's frontier territory, there's always someone looking to make a quick buck. Cue the Martian real estate scams, prime dome-side property. Breathable views, no pesky neighbors for 50 miles. Jokes aside, land ownership in space is a legal minefield. The Outer Space Treaty bans nations from claiming celestial bodies, but it says nothing about corporations or individuals. Could SpaceX essentially become the landlord of Mars? And what happens when rival companies or nations set up their own colonies nearby? The potential for conflict over resources, especially water ice, is very real. Yet for all the challenges, the dream is intoxicating. A backup for humanity, a laboratory for radical sustainability, and perhaps the ultimate test of human adaptability. Whether Musk's timeline holds or not, one thing's certain: the idea of a Martian city has shifted from fantasy to plausible future. And when the first pioneers step onto that red soil, they won't just be explorers, they'll be the architects of an entirely new chapter in human history. Deep in the cosmic graveyard, the corpses of dead stars are acting up, and physicists couldn't be more thrilled. Pulsars, those lighthouse-like remnants of supernova, are supposed to be nature's most precise timekeepers, spinning with metronomic regularity as they beam radiation across the galaxy. But every now and then, one throws a tantrum, a sudden, unexplained speed-up called a glitch. And when it happens, it's like catching a glimpse of the quantum chaos raging inside these ultra-dense objects. Take the Vela pulsar, a 2 trillion-ton neutron star spinning 11 times per second about 1,000 light-years away. It's the poster child for glitches, having hiccuped at least 22 times since we started watching it. One moment it's ticking along perfectly. The next, its rotation rate jumps by a fraction of a second, the equivalent of Earth's day, abruptly shortening by a microsecond. These aren't just quirks, they're cosmic clues. Each glitch suggests that beneath the pulsar's solid crust lies a bizarre quantum soup of superfluid neutrons, swirling with vortices that occasionally unlock and transfer energy to the star's surface. Here's why this matters. Neutron star interiors are laboratories for physics we can't replicate on Earth. The pressures they crush matter into states where atomic nuclei dissolve into a sea of quarks, where protons and neutrons break apart into stranger configurations. When a glitch occurs, it's like the star briefly lifts its veil, offering hints about how these exotic particles interact. The leading theory involves vortex pinning, where swirling superfluid neutrons get snagged on the star's crust like seaweed on a boat's hull. As the crust slows due to magnetic braking, the superfluid keeps spinning faster until the tension becomes too much. The vortices suddenly unpin and the crust gets a speed boost. But not all glitches are created equal. Some are tiny, barely detectable wobbles. Others, like Vela's 2016 event, are monster shifts that rewrite the star's rotation in minutes. Upcoming telescopes like the Square Kilometre Array will catch these events with unprecedented precision, potentially spotting microglitches that last mere hours. Each one is a Rosetta Stone for decoding neutron star physics, and might even reveal whether these objects harbor quark matter or other theoretical states at their cores. The next big glitch could come any day. When it does, observatories worldwide will pivot to watch, because these cosmic spasms aren't just curiosities, they're our only window into the universe's most extreme matter. And with every unpredictable jerk of a pulsar's spin, we're reminded, even in death, stars refuse to go quietly. Remember humanity's first glimpse of a black hole back in 2019. That hazy orange donut, the supermassive monster dubbed M87 star, was revolutionary, but let's be honest, it looked like a blurry screenshot from a 90s sci-fi movie. Fast forward to today, and we're on the brink of a cosmic clarity upgrade. The Event Horizon Telescope Network, the globe-spanning array that captured that historic image, is adding powerful new telescopes to its roster, and their combined vision could soon deliver black hole portraits so sharp they'd make your smartphone camera weep with envy. The secret sauce, raw firepower. The original EHT linked 8 existing telescopes from Antarctica to Arizona, creating a virtual dish as wide as Earth itself. Now, imagine that network supercharged with next-gen additions like the Greenland Telescope and Africa's Millimetron antenna. More eyes on the sky mean more data, and for black holes, data equals pixels. We're talking potential resolutions fine enough to distinguish features just one light day across near M87 star's event horizon. That's like spotting a donut hole on the moon from your backyard. So what's on the wish list for these souped-up images? First up, the elusive photon ring. This razor-thin halo of light, predicted by Einstein's equations, forms when photons skim the black hole's edge, looping multiple times before escaping toward us. Spotting it would be like finding the fingerprint of general relativity itself. Then there's the mystery of M87 star's asymmetric glow. Why does its southern crescent always burn brighter? Some theorists whisper it could hint at a spinning black hole dragging spacetime like cosmic taffy, while others suspect hidden jets knifing through the frame. But here's where it gets wild. Every time we've upgraded our cosmic vision from Galileo's telescope to Hubble, we've stumbled upon the unexpected. Maybe we'll catch a flare from matter being shredded at the event horizon, or spot a star being swallowed in real time. There's even a moonshot chance we'll glimpse subtle distortions revealing extra dimensions or other exotic physics. Skeptics counter that interstellar turbulence might still smear the image like heat haze on a desert road, but that won't stop astronomers from pushing the limits. One thing's certain, these next-gen snapshots won't just adorn textbooks, they'll test whether Einstein's century-old equations hold up under extreme scrutiny. And if they don't, well, that blurry orange donut might end up being the catalyst for the next physics revolution. So keep your eyes peeled. The universe's most enigmatic objects are about to step into the spotlight, and this time they're dressing to impress. For decades, spotting planets around other stars felt like science fiction, but now, we're on the verge of something even more extraordinary, sniffing out their atmospheres for signs of life. The James Webb Space Telescope, with its infrared eyes tuned to the chemical whispers of distant worlds, is about to rewrite the rules of astrobiology. And the key lies in biosignatures, those elusive molecular fingerprints that could signal alien biology at work. Take oxygen, for instance. On Earth, it's a telltale sign of photosynthesis, constantly replenished by plants and algae. Spotting it in an exoplanet's atmosphere would set off fireworks in the scientific community. But here's the twist: oxygen isn't always a smoking gun. Some planets might produce it abiotically through water molecules splitting under intense starlight, for example. Then there's methane, that simple gas cows and swamps belch out on Earth. Alone, it could just mean geologic activity, but pair it with oxygen, and you've got chemistry that shouldn't last long without something constantly replenishing both gases, like life. The James Webb Telescope is hunting these combinations right now, focusing on rocky worlds like those in the TRAPPIST-1 system, where 7 Earth-sized planets orbit a cool dwarf star. Its instruments act like cosmic gas analyzers, breaking starlight filtered through exoplanet atmospheres into rainbows of chemical clues. A single spectral line, barely wider than a pencil mark, could reveal the presence of water vapor, carbon dioxide, or even industrial pollutants from hypothetical civilizations. But the road to discovery is littered with cosmic red herrings. Imagine the heartbreak if we detect methane on a distant world, only to realize it's being spewed by volcanoes rather than microbes. Or oxygen that's not from algae, but from ultraviolet radiation blasting a planet devoid of life. Venus taught us this lesson the hard way. Its clouds once sparked dreams of jungles until we found them seething with sulfuric acid. That's why scientists won't jump to conclusions with a single gas. They'll look for context, seasonal variations in atmospheric composition, the presence of other molecules like nitrous oxide, or even unexpected ratios of isotopes that hint at biological processing. It's like piecing together a planetary crime scene where every trace gas could be evidence of life, or just another dead end. The James Webb Telescope's greatest gift might not be a definitive answer, but a tantalizing maybe. A whiff of something strange, a pattern that doesn't quite fit, and that's where the real adventure begins, because confirming life beyond Earth won't be a single eureka, a moment, but a slow, meticulous puzzle where every piece challenges what we thought possible. And when that puzzle finally clicks into place, it won't just change astronomy, it'll change everything. Deep in the heart of our galaxy, a sleeping giant stirs Sagittarius, a star, the supermassive black hole anchoring the Milky Way. While it may seem like a quiet cosmic vacuum cleaner today, astronomers know better. Every few hundred years, this 4 million solar mass monster wakes up for a snack, unleashing violent X-ray flares that ripple across the galaxy. And the next cosmic belch could be coming sooner than we think. Let's rewind to 2013, when astronomers held their breath as a mysterious gas cloud named G2 drifted perilously close to Sagittarius, a star. Many predicted a spectacular fireworks show, the black hole tearing the cloud apart in a violent feeding frenzy. But G2 surprised everyone. Instead of being devoured, it slipped past with barely a blip on our detectors, stretching like cosmic taffy but failing to trigger the expected eruption. The black hole remained oddly quiet, leaving scientists scratching their heads. But here's what they've pieced together since. Sagittarius, a star, isn't fasting, it's just a picky eater. Observations reveal it flares roughly once every 10 days in X-rays, with occasional larger outbursts. These aren't random hiccups, they're cosmic burps from smaller snacks, asteroids, gas wisps, or even wayward planets falling into its grasp. And while G2 didn't deliver the feast astronomers hoped for, its close call gave crucial clues. The black hole's feeding patterns suggest it might be gearing up for something bigger. Now imagine this scenario: a dense molecular cloud or a stray star wanders too close. Unlike wispy G2, this would be a full-course meal. The resulting flare could outshine every X-ray source in the galaxy for weeks, flooding our detectors with unprecedented data. We might witness the birth of relativistic jets, beams of plasma screaming outward at nearly light speed, or see how the black hole's immense gravity warps space-time during a feeding spasm. The best part, we're finally equipped to catch it. Instruments like NASA Chandra X-ray Observatory and the upcoming European Space Agency's Athena telescope are on high alert, ready to dissect every photon from the next big flare. And when it happens, it won't just be astronomers celebrating. A Sagittarius, a star outburst visible to the naked eye, though unlikely, isn't impossible. Historical records hint that our ancestors might have seen one around the 14th century, a sudden brightening in the galactic center noted by Chinese and Korean stargazers. So when's the next big one? Estimates range from decades to centuries, but with improved monitoring, we might get lucky sooner. Whether it's a modest X-ray flicker or a full-blown galactic roar, one thing's certain: when Sagittarius, a star, finally clears its throat, the entire astronomical community will be listening. And the data we collect could unlock secrets not just about our galaxy's heart, but about how all supermassive black holes shape the cosmos around them. Back in 2015, astronomers stumbled upon one of the most perplexing cosmic mysteries of our time: Tabby's star. A seemingly ordinary sun located about 1,400 light-years away was acting anything but ordinary. This distant star dimmed erratically, sometimes dropping in brightness by a staggering 22% before bouncing back unpredictably. No known natural phenomenon, not planets, not dust clouds, not even swarms of comets, could fully explain its bizarre behavior. The internet erupted with theories, and suddenly the term alien megastructure entered the mainstream. The leading hypothesis: a Dyson sphere, a colossal swarm of energy-harvesting satellites or platforms built by an advanced civilization to capture their star's power. While the idea sounds ripped from science fiction, it's grounded in real theoretical physics. Freeman Dyson himself proposed that any sufficiently advanced society would eventually engineer such a structure to meet their astronomical energy demands. And Tabby's star, with its inexplicable flickering, seemed like the perfect candidate. But before we jump to conclusions, let's break down the science. Natural explanations haven't been ruled out. some researchers argue that uneven dust clouds or shattered planetary debris could still account for the dimming, albeit in ways we haven't fully mapped. Yet, what makes Tabby's star so compelling isn't just the mystery, it's the tantalizing possibility that we might be glimpsing our first evidence of extraterrestrial engineering. Fast forward to today, and new technology is giving us sharper tools to crack the case. Next-generation telescopes like the Vera Rubin Observatory and NASA's upcoming Nancy Grace Roman Space Telescope will monitor millions of stars with unprecedented precision, hunting for similar anomalies. Advanced algorithms will sift through data, distinguishing between mundane cosmic clutter, like rogue asteroids or interstellar dust, and potential technosignatures that defy natural explanation. The stakes are higher than ever. If we find another star behaving like Tabby's, especially one with repeating, artificial-looking patterns, it could reignite the search for extraterrestrial intelligence like never before. SETI initiatives, once sidelined as speculative, are already retooling their approaches, blending traditional radio signal hunts with optical surveys for strange stellar behavior. Imagine the implications. A single confirmed Dyson swarm wouldn't just prove we're not alone. It would reveal a civilization capable of feats beyond our current engineering dreams. Of course, skepticism remains healthy. The universe excels at serving up cosmic illusions, and extraordinary claims demand extraordinary evidence. But whether Tabby's star's secret turns out to be aliens, an undiscovered natural phenomenon, or something even stranger, its legacy is already cemented. It's redefined how we search for life, reminding us that the cosmos might hide its greatest surprises not in radio whispers, but in the flickering lights of distant suns. So keep watching the stars, because the next big discovery might not be a signal but a shadow. China is quietly building a communications revolution, one that could render today's internet as obsolete as the telegraph. By 2030, their ambitious quantum communication satellite network, dubbed Project Jinan, aims to create the world's first unhackable global messaging system. At its heart lies a mind-bending trick of quantum physics, photons that can't be intercepted without leaving evidence. Imagine sending a message so secure that any eavesdropper would instantly alter its very fabric, alerting both sender and receiver to the breach. This isn't science fiction, it's already in motion, with China's Misha satellite demonstrating quantum key distribution across continents since 2017. The magic lies in quantum entanglement, that eerie phenomenon Einstein called spooky action at a distance. Here's how it works. Pairs of photons are linked so that measuring one instantly determines the state of the other, no matter how far apart they are. Encode information in these particles, and any attempt to intercept them collapses their quantum state, like a soap bubble popping at the slightest touch. This creates encryption keys that are theoretically impossible to crack, even with unlimited computing power. Unlike today's encryption, which relies on math problems that quantum computers might soon solve, this system is secured by the fundamental laws of physics. But China's vision stretches far beyond secure banking or military dispatches. The real endgame, a quantum space internet, a celestial web of satellites relaying ultra-secure data across the globe at light speed. Picture autonomous ships, power grids, and stock exchanges communicating with absolute immunity to cyber attacks. Yet where there's technological leaps, there's geopolitical tension. The US and EU are racing to deploy their own quantum satellites, sparking fears of a new Cold War in orbit. After all, whoever dominates this technology could gain an intelligence edge too. Quantum sensors might one day detect submarines by their gravitational disturbances or spy on encrypted classical communications by their quantum footprints. Critics caution that the tech isn't foolproof yet. Atmospheric interference, photon loss over long distances, and the sheer complexity of maintaining entangled states across satellites pose hurdles. And while quantum encryption stops eavesdropping, it doesn't prevent old-fashioned hacking of the computers at either end. Still, the promise is too big to ignore. As these quantum constellations multiply, they won't just change how we communicate, they'll redefine trust, privacy, and power in the digital age. And when that future arrives, the real question won't be whether it's unhackable, but who controls the keys to the quantum sky. Imagine a clock that never winds down, a timekeeping device that ticks perpetually without any energy input, defying the usual rules of physics. That's the mind-bending promise of time crystals, a bizarre quantum phenomenon first theorized in 2012. Now, NASA is taking these enigmatic structures to the ultimate laboratory, space. In a groundbreaking mission slated for the next few years, scientists plan to grow time crystals aboard the International Space Station, where microgravity could unlock their full potential as unhackable cosmic clocks. At their core, time crystals are a new phase of matter that flips traditional physics on its head. Unlike ordinary crystals, which arrange atoms in repeating patterns in space, time crystals repeat their structure in time, like a dance that loops endlessly without the dancers ever tiring. Picture a snowflake that doesn't just sit still but cycles through its shape over and over, like an animation stuck on replay. This isn't perpetual motion, which thermodynamics forbids. Instead, it's a quantum quirk where the crystal's lowest energy state already contains built-in rhythm, making it immune to entropy's usual decay. So why grow them in space? Earth's gravity introduces vibrations and interference that can disrupt these fragile quantum states. In the weightlessness of orbit, time crystals could form with unprecedented stability, free from the jostling that might break their delicate symmetry. NASA experiment will use lasers to nudge a cloud of ions into this exotic phase, creating what amounts to a self-sustaining quantum metronome. If successful, these crystals could become the backbone of ultra-precise atomic clocks, devices so accurate they'd lose less than a second over billions of years. But the real game-changer lies in their potential for unhackable timekeeping. Modern encryption relies on synchronized clocks to stamp digital transactions, and any drift or tampering can create vulnerabilities. A networked array of time crystal clocks, however, would be impervious to external manipulation. Hackers couldn't alter their rhythm without destroying the crystal itself, a self-destruct mechanism baked into the laws of quantum physics. This could revolutionize everything from satellite communications to blockchain networks, creating a celestial time standard that's as trustworthy as the universe itself. Of course, there are skeptics. Some argue that maintaining time crystals outside lab conditions remains a distant dream, let alone deploying them in practical devices. Others question whether their benefits will justify the cost of space-based manufacturing. But if history teaches us anything, it's that today's quantum curiosities often become tomorrow's transformative tech. From lasers to superconductors, the strangest predictions of physics have a habit of reshaping reality. Time crystals might just be the next chapter, a cosmic clockwork ticking silently in orbit, keeping perfect time long after its creators are gone. What if the internet of the future didn't rely on fiber optics or radio waves, but on a beam of particles so ghostly they pass through entire planets without slowing down? Enter the ultimate cosmic messaging system, neutrino communication. These elusive subatomic particles, nicknamed ghost particles, barely interact with matter, slipping through rock, metal, and even you like you're not even there. But their very aloofness makes them the perfect interstellar couriers. Imagine encoding data in a neutrino beam and firing it straight through Earth's core. No cables, no satellites, just an unfiltered line of communication piercing the planet like a needle through fabric. The concept isn't as far-fetched as it sounds. Back in 2012, scientists at Fermilab successfully transmitted a message using neutrinos, encoding the word neutrino in binary pulses that traveled through 800 feet of solid rock before being decoded. Sure, today's neutrino detectors are the size of buildings and require painstaking calibration, but the proof of principle is there. Now scale that up. Picture a network of neutrino transmitters and receivers positioned worldwide, bypassing traditional infrastructure entirely, solar flare frying GPS and radio. No problem, neutrinos don't care. Undersea cables severed by seismic activity, ghost mail delivers. Here's where it gets sci-fi brilliant. Unlike electromagnetic signals that degrade over distance or get blocked by celestial bodies, a neutrino beam could carry data clear across the galaxy with minimal interference. Future interstellar probes might beam updates home through neutrinos, ensuring mission control never loses contact, no matter how many nebulas or black holes lie between us. And for ultra-secure communication, good luck hacking a signal that requires a particle physics lab to intercept. Of course, there's a catch. Today's detectors are about as efficient as catching raindrops with a tennis racket. CERN Ice Cube Observatory in Antarctica, which uses a cubic kilometer of glacial ice as a neutrino trap, might spot a handful of meaningful interactions per day. Hardly the bandwidth for streaming cat videos. But advances in nanotechnology or quantum sensors could shrink the tech dramatically. Some theorists even dream of neutrino lenses that focus these slippery particles into coherent streams, turning a faint whisper into a shout. So while your next email probably won't arrive via subatomic telegram, the potential is too tantalizing to ignore. In a post-apocalyptic scenario where solar storms or war knock out conventional comms, neutrino networks might be the last system standing. And for deep space civilizations, these ghostly messengers could become the universe's ultimate postal service, delivering memos across light years, no return address needed. After all, in a cosmos where even light gets delayed, the particles that barely notice obstacles might just have the final word. The Moon has been Earth's steady companion for billions of years, but its gravitational embrace isn't as constant as we think. Hidden within its orbit is a subtle wobble, a rhythmic sway that takes 18.6 years to complete. For most of that cycle, the effects are negligible. But when the wobble aligns just right with rising sea levels, it's like pouring gasoline on a fire. By the 2030s, this lunar dance is set to amplify coastal flooding to unprecedented levels, turning what were once rare high tides into monthly or even weekly disasters. Scientists call it the lunar nodal cycle, and here's how it works. As the Moon's orbit tilts, its gravitational pull on Earth's oceans intensifies in some regions while easing in others. During the cycle's peak, high tides grow higher and low tides drop lower. Normally, this wouldn't be catastrophic except for one glaring problem: climate change. Sea levels are already creeping upward at alarming rates, with warmer waters expanding and melting glaciers adding billions of gallons to the ocean. When the Moon's wobble hits its high tide boosting phase in the 2030s, cities like Miami, Bangkok, and Mumbai won't just face occasional flooding. They'll endure relentless sunny day floods, where streets fill with seawater even under clear blue skies, no storm required. Visualize downtown Miami in 2035. A full moon rises, and within hours, the famous Art Deco district is ankle-deep in water. Tourists wade through flooded sidewalks while shop owners scramble to install makeshift barriers. These aren't hypotheticals. NASA's own projections show the lunar wobble could triple the frequency of high tide floods in some areas. In places like Norfolk, Virginia, where sea levels have risen more than 14 inches since the 1950s, the added lunar push might render entire neighborhoods uninhabitable at high tide. The irony is that this wobble has existed for millennia, but it's meeting a world radically altered by human activity. Historically, coastal ecosystems could absorb these tidal surges, with marshes and mangroves acting as natural sponges. But after decades of urban development, many of these buffers are gone, leaving concrete jungles defenseless. Combine that with weaker ocean currents due to melting ice, and the stage is set for a perfect storm of lunar-triggered inundation. Yet there's a silver lining. Unlike sudden hurricanes or tsunamis, this crisis comes with a timetable. cities have a few years to prepare, raising roads, fortifying seawalls, or even embracing radical solutions like Venice-style floating infrastructure. The moon's wobble isn't just a warning, it's a countdown, and how we respond will determine whether the 2030s become known for innovative adaptation, or an era when the oceans began reclaiming the land one high tide at a time. Right now, our solar system is cruising through what scientists call the local bubble, a vast cavity in space filled with thin, hot gas carved out by ancient supernova. But this cosmic comfort zone won't last forever. In roughly 50,000 years, we'll drift straight into a dense interstellar cloud, a wall of cold gas and dust that could dramatically reshape our heliosphere, the protective magnetic bubble created by the sun's solar wind. Think of it like sailing into a storm after years of calm seas. This cloud, known as the local interstellar cloud, isn't just a wispy veil. It's a region of space packed with enough material to compress our heliosphere, potentially shrinking it by half or more. That might sound distant and abstract, but the consequences could be anything but. A smaller heliosphere means less shielding against galactic cosmic rays, high-energy particles zipping through space that could bombard Earth with increased radiation. Some researchers speculate this might lead to more frequent and intense auroras, painting the skies with otherworldly colors, but others warn of darker possibilities, like heightened radiation exposure for astronauts, satellites, and even life on Earth. Still, there's no need to panic just yet. Earth's atmosphere and magnetic field provide an extra layer of armor against cosmic rays, meaning life at the surface would likely remain protected. The real test will be for future spacefarers. If humanity is still venturing beyond Earth by then, they'll need advanced shielding to survive the extra radiation. Even our technology could feel the strain. Satellites might experience more electronic glitches, and deep space probes could face accelerated wear and tear from the increased particle bombardment. Yet, this encounter isn't entirely doom and gloom. For scientists, it's a once-in-a-galactic-age opportunity. Watching how our heliosphere interacts with the cloud could reveal secrets about how stars and planetary systems evolve in dense regions of space. It might even help us predict what happens when other star systems pass through similar clouds, knowledge that could prove vital if humanity ever colonizes distant worlds. So, will this interstellar rendezvous be a light show or a cosmic crisis? The truth is, we won't know for sure until we get there. But one thing's certain: the universe never stops moving, and neither do we. Whether it's 50,000 years from now or 5, our solar system's journey through the galaxy is far from over. And when we finally enter that interstellar cloud, it'll be another reminder that even in the vastness of space, change is the only constant. Every night, telescopes around the world capture avalanches of cosmic data, so much that no human team could ever sift through it all. That's why astronomers are turning to artificial intelligence, training algorithms to spot the subtle, the strange, and the statistically impossible hiding in the noise. And someday soon, one of these AI scouts might flag something that defies every textbook in existence. Think of it like this: you've spent years listening to a symphony, memorizing every note, then one day, the violins play a chord that shouldn't exist. That's the moment we're waiting for. Machine learning systems, fed on decades of stellar behavior, galactic rotations, and quantum patterns, are now scanning the skies for anomalies that would make even the most seasoned astrophysicists double-check their equations. The James Webb Space Telescope alone generates terabytes of data weekly. Without AI, we'd be drowning in undiscovered mysteries. But here's where it gets thrilling. Unlike humans, AI doesn't come with preconceptions. It doesn't dismiss faint signals as probably just noise or assume odd light curves must be instrument errors. In 2018, an AI combing through Kepler Space Telescope data rediscovered a star system with 8 planets, something humans had missed because the signal was buried under layers of noise. Now imagine that same tool stumbling upon a galaxy spinning too fast for its mass, or a star emitting pulses in a sequence that looks suspiciously intentional. Of course, the universe loves playing tricks. 99 times out of 100, these anomalies will have mundane explanations, instrument glitches, unresolved background objects, or statistical flukes amplified by overeager algorithms. But that 1%, that's where revolutions happen. The discovery of dark matter began with Vera Rubin noticing galaxies rotating weirdly. Pulsars were first flagged as LGM signals because their precision seemed artificial. AI could be the tool that uncovers the next great cosmic "what the heck is that" moment. Critics argue we're setting ourselves up for false alarms that will chase digital phantoms while real discoveries gather dust. But the alternative is worse, missing something extraordinary because it didn't fit our expectations. Whether it's evidence of higher dimensions, a flaw in general relativity, or, let's be bold, a signature of alien engineering, one thing's certain: the first AI-detected cosmic anomaly won't come with a label. It'll be a single line of code raising its hand in the dark, whispering, "Hey, you might want to look at this," and when that happens, the real mystery begins. Right now, hundreds of thousands of bullet-speed debris fragments are zipping around Earth, everything from dead satellites to discarded rocket parts and even flecks of paint. Each one is a potential wrecking ball capable of shredding multi-million-dollar spacecraft in an instant, and we're barreling toward a breaking point. By the 2030s, experts warn we could hit the Kessler syndrome, a catastrophic chain reaction where one collision spawns hundreds of new fragments, each triggering more crashes until entire orbital highways become impassable. Picture this: a single screw traveling at 17,000 miles per hour smashes into an old satellite. The impact creates a cloud of shrapnel which tears through a weather satellite, then a communications array, and suddenly, low Earth orbit is a minefield. Rockets can't launch without risking instant destruction. GPS fails, climate monitoring goes dark. The International Space Station might even need to evacuate. This isn't dystopian fiction, it's a scenario with eerie precedent. In 2009, a defunct Russian satellite collided with an active American one, scattering over 2,000 traceable fragments into orbit. Worse yet, in 2021, Russia's anti-satellite missile test added another 1,500 pieces to the chaos. But here's the twist: space junk grows exponentially. Every new collision doesn't just add debris, it multiplies the risk of future impacts. By some estimates, we're just one major accident away from triggering irreversible cascades. Enter the cosmic cleanup crews racing against time. Startups like Astroscale are testing magnetic tow trucks to latch onto dead satellites and drag them into fiery re-entries. Others are experimenting with nets, yes, literal nets flung into orbit to ensnare floating junk like interstellar fishermen. Then there's the most sci-fi solution of all: lasers. Ground-based beams could nudge debris onto safer trajectories by heating their surfaces, creating tiny thrusts without physical contact. Japan's Star Lab even proposes coating junk with reflective paint to enhance laser pushing power. Yet for every high-tech fix, there's a gnarlier snag. International law bans weaponizing space lasers, blurring the line between debris zapping and anti-satellite tech. And who foots the bill? The companies creating mega-constellations of satellites, like SpaceX's Starlink, argue they shouldn't bear sole responsibility for cleaning up decades of global clutter. Meanwhile, legacy debris, like the derelict Soviet-era rockets still circling Earth, poses legal headaches since no one owns them anymore. The clock is ticking. The European Space Agency estimates that even if all launches stopped today, collisions would keep increasing debris for centuries. But here's the sliver of hope: this crisis could spark unprecedented cooperation. Imagine a global orbital traffic control system where every satellite shares real-time positioning to dodge disasters, or treaties mandating end-of-life deorbiting, turning dead spacecraft into self-cleaning ephemeral tools. The 2030s might be the decade we lose access to space, or the one where humanity finally grows up and starts tidying its cosmic backyard. Either way, the choice is ours, and the window to act is slamming shut faster than we think. Picture the universe stretching itself thin, not just expanding at the edges but unraveling at the seams until galaxies, stars, and even atoms are torn apart in a final, unfathomable instant. This nightmare scenario, known as the Big Rip, represents cosmology's most dramatic doomsday prediction, a point where dark energy, the mysterious force accelerating the universe's expansion, grows so dominant that it overpowers gravity, electromagnetism, even the nuclear forces holding matter itself together. But here's the twist: whether this cosmic apocalypse happens at all hinges on a single, unresolved question: what exactly is dark energy? Right now, the leading model treats dark energy as a constant, an unchanging force woven into the fabric of space-time. But what if it's not? Some theories suggest dark energy could intensify over time, growing stronger as the universe expands. In this scenario, roughly 22 billion years from now, its grip would become so overwhelming that galaxy clusters would first disband, then individual stars would be ripped from their systems. Planets would disintegrate, molecules would fly apart, and finally, in a split-second atomic nuclei themselves would burst asunder. The universe wouldn't just fade into cold darkness, it would be shredded into a soup of lone quarks and radiation, unable to ever reassemble. Yet not all cosmologists are convinced. A rival camp clings to a far cozier vision, the Big Crunch. Here, dark energy weakens or reverses, allowing gravity to claw everything back together in a cosmic U-turn. Imagine all of existence collapsing inward until galaxies merge, temperatures soar, and space itself contracts toward a fiery singularity, a mirror of the Big Bang and possibly the seed of a new universe. Some versions of string theory even suggest this cycle could repeat eternally, with universes breathing in and out like lungs. But how soon might we know which fate awaits us? Surprisingly, the answer could come much sooner than billions of years, possibly within the next century. Next-generation telescopes like the Vera Rubin Observatory and the European Space Agency's Euclid mission are hunting for subtle clues in the stretching of spacetime itself. By precisely measuring how fast the universe's expansion accelerates and whether that acceleration is changing, we might finally crack dark energy's code. A slight deviation from current predictions could tip the scales toward rip, crunch, or even a third option: the Big Freeze, where dark energy remains constant and the universe simply expands into eternal, lonely stillness. The stakes couldn't be higher. If dark energy's strength varies even slightly, the difference between a universe that dies screaming and one that recycles itself could come down to numbers smaller than anything we've ever measured. And while our own civilization won't be around to witness the finale, the knowledge of how it all ends would redefine humanity's place in the cosmos. Are we fleeting sparks in an inevitable void, or witnesses to the first act of an endless cycle? The answer might be written in the darkness between the stars, waiting for us to decipher it. From colliding neutron stars forging gold in cosmic furnaces to rogue interstellar objects that might just be alien technology, we've raced through the most mind-bending cosmic events set to unfold in our lifetimes and beyond. Betelgeuse could light up our skies with a supernova visible in broad daylight. The moon's wobble might drown coastal cities under routine floods. And who's to say the next anomaly spotted by AI won't rewrite the laws of physics? But here's the fun part: these aren't just predictions, they're invitations to wonder. Will Elon Musk's Martian metropolis rise before we crack the quantum code of time crystals? Could a Dyson sphere discovery or a neutrino message from deep space steal the spotlight? The universe loves a good plot twist, and the comment section is your stage. Drop your bets below. Which event are you marking on your cosmic calendar? And stay tuned, because the cosmos never plays by script. For every event we can predict, there are 1,000 wild cards lurking in the void. Solar flares that rewrite satellite histories, black hole mergers that rattle spacetime. Our next dive will explore the utterly unpredictable. Until then, keep looking up. The universe has a way of outshining even our wildest imaginations. Don't miss what's next. Hit subscribe and let's unravel these mysteries together.